So hello, my name is Susie Newhan and I'm going to be talking to you a little bit about differentiation. It's just a very initial look at differentiation, what it's all about. I'm not going to be able to teach you in this video how to do it. I just want you to get a sense for what it is and how it's used. And then in the next video, I will teach you a little bit about how to do it at a fairly basic level, but you will at least be able to differentiate after the next video. So let's have a look at this. So I want to start by talking about small changes. So in economics, we talk a lot about small changes. And here's some examples. I'm not going to read them. But it's all about what happens if we make one small change to one aspect of what we do. What if we hire one more worker? How much extra productivity would we get out of one more worker? How much extra profit would we get from making one more product? Should a firm take on one more order? Yeah, it's this idea of making a small change and seeing what happens to the other variable. And the word you will see a lot now is marginal. We're talking about making marginal changes. So we're talking at a particular level of production, the one we're at now. If we make a small change to that, what will that do to our profit? And that will give us the idea of marginal profit. So we're not interested in the first product we make. That's different. That's got a lot of extra costs in it. We're talking about making a change from where we are now. So all these are about marginal change. Now, in economics, marginal changes are used a lot. So here's just a couple of examples. Marginal cost, which is the cost of producing one more unit above or below where we are now. Marginal utility, the change in utility we get from one unit increase or decrease in our current level of consumption. So there's lots of ways of saying marginal cost. So here's just some different ways of expressing it, just different use of language. So it might be expressed as the rate of change of cost, the cost of adding one more item, the rate at which cost changes as quantity increases by 1, that's a pretty good definition. The rate of change of cost with respect to quantity, that's a sort of differentiation way of expressing it. But they all mean the same thing. And here's a couple more. Phone going off. And here's a couple more, but we're not going to look at those in this video. Right, so I just want to remind you a little bit about gradients, because gradients are quite important in this discussion of differentiation. So there's a little bit of revision. Okay, a reminder that gradient is defined as the change in the vertical dimension. We normally think of that as the y variable, but in economics it might be something else other than y. It might be total cost. But gradient is the change in y over the change in x. And you'll remember in our lecture we were counting squares to calculate the gradient. So that's just a reminder. So let's have a little practice. So here's a line going through 2 coordinates. We want to know the gradient of that. So we're either going to look at subtracting the y coordinates and the x coordinates, or we're going to count squares, actually the big squares. As we went from b to a, y got bigger by 3, and x also got bigger by 3. So it's 3 over 3. The change in y over the change of x equals 1. So this has got a gradient of 1. That's why it looks 45 degrees. So we can infer from this that y will increase by 1 each time x increases by 1. So the rate of change of y with respect to x is 1. It will move in concert with x. What about this one? What's the gradient of this line? Well, the y coordinates went from 1 to 3, so the change in y is 2. And the x coordinate went from -2 to 3. So if we count squares, that tells us it's changed by 5. So the gradient is 2 over 5, or 0.4. Or we could subtract the original value of x from the new value of x. So we ended up at 3, and we started at -2. So we say 3 minus -2, and when we have a double minus like that, it's the same as adding. So it works numerically as well as counting squares. Counting squares is definitely easier. Okay, so we've got a gradient of 0.4, quite shallow. That's why the gradient is less than 1. And we can tell from this that every time x increases by 1, y will increase by 0.4. So the marginal rate of change of y is 0.4. What about this one? This one we note we're leaning in the other direction. This is going to give you a negative gradient. And whether you end up with a negative on the top or the bottom is determined by where you started from, but it doesn't matter. We could say that the value of we could say that from here to there, the value of x decreased from 3 to -3, so the change in x is -6, but the change in y is +3. The y value went from 1 to 4. Or if we looked at it coming from there to there, it would be -3/6, but either way it's -0.5. So you just got to be careful when the gradient, when the slope of the line is backward leaning like that, it's a negative gradient. It means that as x is getting more positive, y is getting more negative, and vice versa. So from this we can see that y will decrease by will decrease by 1/2 each time x increases by 1. So we either say it decreases by 1/2 each time x increases by 1, or we can say it increases by -1/2 each time x increases by 1. In any case, it's going to go in the opposite direction from x because it's a negative slanting line. So we probably don't need to go through these, but some little extra practice here. What's a gradient of a to b? Well, the difference or the change in y is 1 over the change in x is 4. So the gradient is 1/4. It's a shallow gradient, so it's less than 1. Gradient of a to c, the change in y value is 4 over the change in x value, which is 1. So much deeper, gradient of 4. Gradient of CB is a negative gradient, backward slanting. Now, so the change in y from C to B is -3. Y has gone down by 3, but x has increased by 3. So we've got -3 over +3 equals -1. And just a few notes on those, but we've already talked about those. So now I just want to talk a little bit more about rate of change. But before I do that, here's a definition of tangent, a line that touches a curve at a particular point. So the yellow dot there is the point of tangency where that line touches, just briefly touches the curve. So now I want to sort of get you thinking more of gradients as rates of change, because that is what they are. This graph here is plotting a car's journey. On the x dimension we've got seconds, and here on the y axis we've got meters, and we found that in 5 seconds it's gone 40 meters. So we can look at this rate of change, and the rate of change at which distance changes with respect to time is called speed. Thankfully it's got a shorter term for it, the one that we use every day. So speed is the rate at which distance is changing with respect to time. And because it's a straight line, it's relatively easy to find speed because it's just the gradient of that straight line. So the gradient is change in y, which is here change in distance, over the change in x, change in time. Same old, same old. So we're getting the gradient. That's 40 over 5, which is 8. So the gradient is 8 meters a second, which is the speed, because the speed is the rate of change of distance over time. And because it's a straight line, the rate of change is not changing. It's a constant rate of change. So there are many applications of gradient as representing the rate of change. Some you're familiar with, some you're not. But what if the gradient is not constant? There it's a much more complex situation. But we still want to find the rate of change of whatever it is at a particular point. There's so many times that we want to do that, particularly in economics. Remember, we were talking about small changes from the current level of output. So we want to be able to pick an X value and say what's the marginal change at that point. So we need a way of doing this. We could try drawing tangent lines and sort of calculating the angle or the gradient of the tangent, but that would be so inaccurate. If you try that, put your ruler on that curve, you just don't know which angle to put it at. It just doesn't work. We need another way of doing it. Oops. Did I go up too many there? No. You see, and this chart is hopefully going to show you why it's such a problem, because look what happens to the gradient of this curve. This is the curve, here's the gradient. Look what happens as we move along the curve. It's forever changing. Look at that, the gradient's changing everywhere. So we need a very accurate way of telling us the rate of change or the gradient at any point on that curve. Look what happens to the gradient when I come over the hump. Ooh, just for a moment it goes to 0. Oh, I missed it. And now it's coming down again. See, here it's a positive gradient, but once I go over that bump, remember I talked about backward leading gradients, there's a negative gradient there. As it comes here, just around the bottom, it's going to just briefly touch 0, and there it is, and now it's going to increase, steeper positive gradients, but it's changing everywhere on that line. This is the problem. The gradient keeps changing. So this process of finding the rate at which the variable changes at any point on the curve is called differentiation. So it's going to allow us to find the gradient of the curve at any point. So as I said, on this video, we're not going to see how to do it. I just want to show you the results of it. So here's a diagram of y equals x squared. And it turns out that when we differentiate y equals x squared, we get this other function. So differentiation always gives us a second function. And this function is called dy by dx. Actually, it's got lots of names, but we'll call it dy by dx. It's also called the first derivative, the differential. So the function we get when we differentiate this is dy by dx equals 2x. Now, it doesn't look any great shakes, but this is amazing because this is the gradient function, and it tells us the gradient anywhere on this curve if we just substitute the value of x at a particular point. So if we're interested in what is the gradient of this curve when x equals 1, we just substitute 1 in that x value and we'll get 2 times 1, and we find that here the gradient is 2. I mean, can't get much easier than that, can it? So here's some examples. So for instance, when the value of x is 0, which is one of these turning points, one of these minimum points that we looked at on the previous slide, when x is 0, the gradient will be 2 times 0 because it's always 2 times the value of x, so it's 0. So even if we didn't have a diagram in front of us, we would know that when x is 0, there's a turning point because the gradient is 0 at that point. When x is 1, here it turns out that the gradient is 2. When x is 3, off the chart up here, the gradient is 2 times 3, which is 6. So we can see the gradient is getting steeper. But the point is, whatever value of x we substitute into 2x, that will give us the gradient at that point on the curve. So we can't get more accurate than that. And because we know the gradient, we also know the rate at which y is changing when x changes by 1 at any point on this curve. So as we said, when x is 1, the gradient is 2. So this tells us at this point there, just at that point where x is 1, y is changing by 2. By 2 each time we make a change. So just instantaneously there, the rate of change is 2y. and i.e. we've straight away got the marginal rate of change of y at any point on that curve. So once we know how to differentiate, this is the kind of thing we get. It's really, really helpful. So just a note about calculus. You'll hear that word a lot. Calculus is a branch of mathematics. It breaks down into two areas: differentiation and integration. We don't see much integration in economics. It's about areas and accumulation. So we're not going to talk about that now. But we do see a lot of differentiations because we're interested in marginal change, rates of change, gradients. We're interested in that whole thing. So we often use this word infinitesimally small in the study of calculus. What we're doing to give us as much insight as possible, we make infinitesimally small changes to, say, the x variable and see what that means to the y variable. And just a note there, it takes a lot of algebra to understand why it works, and I'll give you a taste of it in the next video, but it's quite easy to understand how to use it.